It's time for another amazing chemistry video with Mr. Stapleton, proudly sponsored by Farmers Union Nice Coffee. Okay, welcome to subtopic 1.3 in the first topic for Year 12 Chemistry. This one's all about volumetric analysis or titrations basically. Now I'm going to fly through these notes reasonably quickly because hopefully this is a bit of a recap of Year 11 work, but there are plenty of video links to my other YouTube videos that you'll see throughout this, so I suggest if you need more help that you go to those. But basically, just to start recapping, there's two types of analysis we can do, which was qualitative, working out what something is, so that what the quality, and quantitative is working out how much of it there is. And if you don't have an understanding of the mole, I really suggest that you do a little bit of research or do a bit more reading about it. But basically, the mole is a unit of measurement for chemistry. And what we say that for 1 mole, that is 6.02 by 10 to the 23 atoms of anything. Okay, or it could be 6.02 by 10 to the 23 molecules, for example. So there's a couple of different examples which you can have a look at, but I'm not going to spend too much time on it now because, like I said, hopefully it's a recap of Year 11, and if you need to, maybe go back and have a look at one of the videos of the basics of chemistry that you need to get a handle on. The other thing you need to be aware of when we're looking at titrations is the concept of significant figures. Okay, so what I'll go through here for significant figures is just that if they're to the left, they're not important at all. So none of these ones here we count as significant. Okay, we only count the ones to the right. Generally, these ones on the right we do count as significant. So this one here, 234,000, we would generally say has 6 significant figures, and this one here, 0.015700. we would always probably say that has 5 significant figures because there's no point writing these zeros here unless they are significant. So that would be 5 significant figures as well. If you need more help on significant figures though, make sure you do check out the YouTube clip over here, which you can click on as well. When we're doing titration calculations, and this is the key you need to understand, is that when we are doing them, we always give our answer to the least accurate piece of apparatus that we are using. So if we were doing a titration using the apparatus that's here on the screen, this pipette, burette, volumetric flask, and mass balance, you can see up here the pipette is the least accurate one at 3 significant figures. So any answer that we would give there would be to 3 significant figures for a titration. So what I suggest you do when you've got a question for titration is you actually highlight each of the values you get and you write next to it how many significant figures you have. Now I always shorthand it, so I write something like this, 3SF, so 3 significant figures. And then I remember which one has the least accurate, and that's what I give my value to. We also want to talk about resolution when we're doing titrations because you've got different pieces of glass where they have different resolution. Basically, resolution refers to how many decimal places it can go to. So the more decimal places it can go to, the higher the resolution of the image as well. Now, if you don't have an understanding of random systematic errors, I really recommend that you use the YouTube link, which will be coming up. All right, but I'll just go through it really quickly. All right. In titrations, we want to perform titrations and we want to get the same titer value every time. So coming out of our burette, we want to make sure we've got the same volume coming out every time. That if we do that, that means we're precise and we've minimized any of our random errors that we're using. Now, random errors happen only once. All right, so once off things. So I've got some examples of it shortly, but those random errors affect our precision. So that's how close our values actually are to each other. So some examples of random errors are things like misreading the burette. So if you've got your burette and so here's your burette, all right, and there's your meniscus there. If you're looking at it from underneath, for example, the value will appear higher than it actually is. And so that's going to be an error that you've done, which will affect your later on values. For our titrations, we also want to get the first permanent color change at the end of our titration. So if you go too far from that, if you go over it, your value is going to be higher than what the actual titer value should be, which will affect your value as well, your final calculation. And if you don't transfer all the solid into your volumetric flask, you're going to base your calculations based upon what you weighed out. However, you didn't use all of that in your standard solution, and so it's going to affect your final value as well. We can, now probably the better terminology to use, rather than reducing random errors, we can actually minimize them. So we minimize random errors by repeating the measurement a large number of times and averaging the result. The more we reduce the risk of them, the more precise the results will be, so the closer they are and the more likely are we're going to get concordant titers. If you're talking about accuracy, accuracy is how close you are to the final value. Okay, so you'll do your titrations, you'll go through and you do all your calculations to get a final value, and then compare that to the known value of it. And the closer you are to the known value, the more accurate you are. The accuracy is affected normally by systematic errors, so they're sometimes called apparatus errors or glassware errors, and they're due to errors normally with the instruments or glassware that you're using inside the practical. What that means is that will happen every single time you do it, and so they will happen systematically, and that's where the name comes from. They can be minimized by repeating the experiment with a completely different set of apparatus. So if, for example, a really good example is if you got a pipette that you believe is 20.00 milliliters, let's say, for example, that when it was being formed, there was a slight deformity within the glass or something, and it's actually 20.02 milliliters. What that's going to mean is that all your calculations are using this value, but you're actually delivering this much in your titration. So it's going to make your answers less accurate than they should have been. So the way you get rid of that is you use a new pipette, hopefully, which is exactly calibrated to 20.00 mils, and that will make sure that your value is more accurate. There's some other examples over here which you can have a look at as well. And what I strongly recommend you do if you need more help with random and systematic errors is use this YouTube video, which has gone into a bit more depth, and it goes through a lot more of this sort of explanation. So I'm not going to go into more depth here, but I encourage you to look at that if you need to. You can see random systematic errors on graphs. The best one you can see is random errors. So if you have a line of best fit, which is this one, so this is our line of best fit, okay? What you can see here is each of your points are scattered around the graph. So there's what we call a high scatter here. Now that high scatter indicates the presence of random errors. If they sat nicely on the line of best fit like this, we would say there was very little scatter and there would be no random errors. But because there's a fair amount of spread there or scatter, they are in fact due to the presence of random errors. Now, not every graph that you're going to draw is going to go through the origin. However, if this one was meant to go through the origin, you can see our line of best fit clearly doesn't. If it doesn't, that normally means that there's a presence of systematic errors, but that's only if it should go through there, and not every graph will. So just be careful about stating that there's systematic errors. Think about the relationship first before you state that. So what we got into is the actual calculations for stoichiometry. Okay, so this is the first triangle you need to know, and there's two of them. Okay, so this triangle is for our first calculations. This is the basis of our stoichiometry. So N is a number of moles. Okay, and that's generally what we're calculating using this one. M is mass, and the mass is always in grams. Okay, and big M is the molar mass, and the molar mass is in grams per mole. Okay, so the way I tell my students to remember this is that the number of moles is birds over mountains. So obviously I'm quite rubbish at art. So when I used to draw birds, I used to draw them like this, like an M. Okay, and so there's birds flying over mountains. If you remember, that's an easy way to do it. Now, to calculate the molar mass, we add up all the relative atomic masses of the atoms from the periodic table. Okay, so if we want to calculate how many moles are in 1.3 kilograms of ammonium phosphate, okay, well, I'll show you how we do that. Okay, so to calculate the molar mass, we need to add up the relative atomic masses of each of the atoms up here in the ammonium phosphate. So what we've got is 3 nitrogens, which are 14.01. We want to add to that. We've got 12 hydrogens, because there's 3 lots of 4, so there's 12 lots of hydrogens, which is 1.08. We want to add in a phosphorus, which is 30.974. And then we want to add in 4 lots of oxygen, which is 15.999. So if you do that calculation, add them all up, okay, I apologize for my dodginess of my writing, you get 149.096 grams per mole. So that's the molar mass of ammonium phosphate, which is 1 mole of ammonium phosphate. So what we do to calculate the number of moles is we use our number of moles is birds over mountains. Okay, so our mass is 1.3 kilograms, so we need to put our mass into grams, so 1.3 times 1,000. We divide it by the molar mass, which is 149.096, Okay, and what we do is we're going to give our answer to two significant figures because there's only two significant figures given up here. So the answer is 8.71. Whoops, I've done too many, haven't I? It's 8.7 moles. Okay, so that's two significant figures, and that's how you use the atomic masses off the periodic table to calculate a molar mass, and how you then use that to calculate a number of moles. Later on, there's a link to a whole bunch of calculation videos I've done. I suggest you have a look at those for a bit more practice of these. So once we've done a number of moles calculations, we normally use that to then do our concentration calculations, and this is the second one that we use. If you can remember, concentration is moles per litre. So this is number of moles, with the units is mole, okay? And this is our volume, which is in litres, okay? So if you can remember concentration is moles per litre, you'll be able to remember this one as well, okay? This is a table of conversions that you might want to use. So the common ones that we often use are this one, grams per litre. So to get from moles per litre to grams per litre, we times by the molar mass. Okay, and to get to something called percentage weight per volume, we divide by 10. So this is quite common within foods, for example. You also get percentage weight per weight and percentage volume per volume. So all of these, because they're a percentage, they're out of 100. All right, so instead of having however many grams we've got per litre, we have how many grams we've got per 100 mils, which is what percentage weight per volume is. Percentage V per V is what you'll find often in alcoholic drinks. Okay, so they'll talk about, for example, 30% volume per volume. So that means there's 30 milliliters of ethanol in every 100 mils of the alcoholic drink. And so that gives an example of how they calculate standard drinks. These other ones, parts per million and parts per billion, you need to know as well. All right, just moved my video, sorry. And so just make sure you can do those conversions and you understand what they are. So parts per billion is micrograms per litre, and parts per million is milligrams per litre. Okay, so you can actually do those conversions as well. There's lots, again, practice of those in the videos, so I suggest you have a look at them. So what I cannot stress strongly enough is the fact that anytime you're doing stoichiometry calculations, you follow these steps. The first one in particular is really important because if you don't get this right, you won't get part 4 right, all right, and then you won't get your final answer right. So you've got to practice your equations. Then you write down what you know, all right, and so I go through that in the videos. You work out number of moles for the known. That's the one when you write down everything you know, it's what you've got the more values for. Then calculate your mole ratio using the equation, work out number of moles for the unknown, and find the answer. Okay. So as again, I'm not going to go through this in any more depth apart from to say, look at the videos I've done. Okay. Now, titration glassware that we use. Okay, when you're actually doing a prac. Okay. Again, there's some information here about what we actually do for preparing the glassware. All of this, okay, is in this YouTube video. So I go through an entire titration there. I make up a standard solution. I talk about rinsing of the glassware and I say why we do it. So I'm not going to go through much more depth in this apart from to say that we always rinse our glassware firstly with distilled water. That removes any impurities from the previous experiment. Okay, and what that does is that prevents a systematic error occurring where we've got a concentration that's lower than what we're actually using or calculating. Okay, what we then do for the burette and pipette over here is we rinse them with the solution that's going into them. That prevents dilution from the water. So if you didn't rinse them with the solution going into them, then the water that we rinsed it with would dilute it and again cause a systematic error. Okay, so the burette we've got here talking through, and this is how we use the burette. As I said, I cover it all in the video. Okay, pipette, again, I cover it all in the video and the correct way to do it. So make sure you know those techniques because you can get asked about them in the exam. I said at the beginning of that, I also make a standard solution. And now all you need to know is that a standard solution is a solution of known concentration and purity. All right, and we must use an analytical grade reagent. So an analytical grade reagent is basically one that doesn't absorb moisture from the air, doesn't react with other things, it's very stable. Okay, again, like I said in that practical video, the link back on the first page, I go through creating a standard solution first. So I suggest that you watch that if you need more info. So if you've got an understanding of how to use your glassware and you're ready to do a titration, you understand where your systematic and random errors can come in, you're basically ready to start doing your first titration. Now, when we record results, you should always set it up in a ruled table like this. All right, have your title values across the top. Now, the reason I set it up this way of final and then initial is just so you can take the initial from the final and get your final value. All right, so normally for your first one, you would set up your initial value to be 0.00 on the burette, and you might go, for example, 21.22, for example, or something. And so you can just do a title value of 21.22. Then what you can do is transfer that value straight over 21.22 because you know your burette holds 50 mils, and you can keep going up to the next one, which will say be 42.45. And so you can just do 21.2, take 40 away from 42.45 to get a value of 21.23, and you can just keep going and filling out your table. Okay. Important thing to remember is you can always read your burette to 2 decimal places, so make sure you do that. And when you set up a table like this, it allows you really easily to see your concordant titles that you've got. So, like I said, I've gone through this one reasonably quickly because there are a lot of videos through here that you can have a look at. And if you click on this one here, I think that takes you to a playlist with about 8 different titration calculations. Okay, and those ones will be kind of a recap of year 11 titration calculations. When you've got a handle on those and you reckon you can do them pretty easily, I then suggest you go on to this one and you start doing some back titrations. Right? Because back titrations are really what we do in Year 12 chemistry, which is using a titration to go backwards to another reaction to work out initially what we had. So best way I can explain that is for you to have a look at this video. Okay, really recommend that you do it. And hopefully that will help you get a really good understanding. If you can follow that video there on back titrations and follow the calculations, you'll be set for Year 12 chemistry. But my advice is if you don't get it, keep calm, try it again, and I'm sure it'll come to you. All right, that's the end of this one on volumetric analysis. There's 2 more videos on this first topic. So once you've got a handle on this, I suggest you move on to them. But as always, if you've got any questions, just ask. Thanks, guys.